In lecture 20, we shall discuss the Lagrange's equation of motion. In fact, particularly, we will call it the Lagrange's equation of motion of second kind. So, the mainly two things we are going to discuss here. One is the Lagrangian equation of motion of second kind, and second is Lagrangian equation of motion for cyclic coordinates. So, first, we derive the Lagrangian equation of motion of second kind. So in the form of a theorem, if we give the statement of this theorem, it is like that: derive the Lagrangian equation of motion, Lagrangian equation of motion. And this Lagrangian equation of motion is just like the Euler's equation in calculus of variations. Okay, so here the parameters related to the dynamical system will be involved, and in that case we have seen the um, derivation of extremal of a function. So the main thing is Lagrangian equation of motion. So in this part, in classical mechanics, it plays very important role, and most of the numerical problems will be done with the help of this Lagrangian equation of motion. So we derive the Lagrangian equation of motion for holonomic system specified by certain generalized coordinates. Or it can be stated alternately in this way: establish the Lagrangian equation of motion for a holonomic dynamic system in the form d by dt del t by del qj dot minus del t by del qj, that is equal to this qj, where j going from 1 to n. So here T is the kinetic energy of the system at time t, and Qj are the generalized forces specified by n generalized coordinates Qj, j going from 1 to n. So this equation, in fact, this equation is called the Lagrangian equation of motion of second kind. So here we have already discussed these notations that Qj's denotes the generalized coordinates, and Qj dot in fact is del Qj divided by del t, that is the generalized velocity. So if you have a system of in fact uh, n particles, that you are having p1, p2, these are the n particles, and so on, pn, then for these you have denote it by r, the position vector, and this is r1, this is rn, this is suppose r2, and similarly here this is by r1, this is the position vector. And the position of the generalized coordinates corresponding to these are given by q1, q2, and so on, qn. These are the n generalized coordinates, and if there is involvement of time, t is there. And Qj, you know, the generalized force we have already described in lecture number 19. Fine. So now we are going to derive this Lagrangian equation of motion of a second kind. So how is that? You see the proof. Let Ri be the position vector of the ith particle having mass mi. Because here I have mentioned this system of n particles, and suppose somewhere there is ith particle pi, and its position vector is given by ri. So if position vector is ri for the ith particle and it has the mass mi, then by Newton's second law of motion, what do we have? The force is equal to mass into acceleration for the ith particle, because you are talking about only the ith particle. Suppose pi is here, and this position vector is ri for this ith particle, and the mass of this particle is mi. Mass of this particle is mi. Then by Newton's second law of motion, you know that the total force on a particle is given by mass into acceleration. And here we already know that one of these Fi is internal force, and one of these is the external force on the ith particle. The total force is Fi plus Fi dash. and that is equal to mass of that particle, and Ri double dot means the acceleration. Ri is the position vector, then Ri dot, in fact gives you the velocity, and Ri double dot gives you the acceleration. So that is why here we are writing mass into acceleration. This is according to Newton's law of motion, and I equal to 1 to n. It denotes the number of particles in fact in the system. So dot represents the differentiation. You know the total forces according to Newton's law is mass into acceleration. That is why this equation has been obtained. Now, if you multiply on both sides with this term del Ri by del Qj, and also in right hand side del Ri by del Qj, you call this as equation number 2. And in fact, this is equation number 1, and this is equation number 2 here. Fine. So now we can see this equation number 2 is here. Equation number 2 is here. Then if we consider this term, because we want to simplify this equation further, if we consider this term d by dt of Ri, why I am taking this term, you will be able to understand at later stage. Ri dot into del Ri by del Qg, derivative of that if you are considering. Then by product rule of derivative, derivative of first, that is Ri double dot, and second term as such. Further, you will write the first term as such and the derivative of the second term. So derivative of second term you are getting like this. Now you are calling this equation as number 3. Further, we know that we have proved this thing, that del Ri dot by del Qj is equal to d by dt del Ri by del Qj. It has also been proved. So you use equation 4 in 3. That means somewhere you are having this d by dt del Ri by del Qj. So in place of this, you can write this quantity. In place of this, you can write this quantity over here. And consequently, this equation number 3 becomes like this. When you substitute here, this quantity, you are putting in place of this, this value, del Ri by del Qj, you are substituting here. In fact, you see, again, we move on to the last slide. Yes. So if you substitute this d by dt del Ri del Qj here in 3, so let us see what do we get. Left hand side is as such, Ri double dot del Ri by this Ri dot, and in place of this you will substitute this value, from where this minus sign is obtained. In fact, I think this should be the plus sign either here. Let us see. So if you are having Ri double dot del R by this, yeah, in fact, we are getting in this way. This quantity is there, and we take this quantity on this side, so that we get d by dt of this quantity minus of this quantity, in fact, the value is substituted, this one, del Ri dot by del Qj is there. So in this way, we are getting this equation number of 6. Now, using 6 in 2, we get, using 6 in 2, we replace in 2, we replace this quantity by this quantity. So equation 2 becomes this, and this is equation number 7. If we take the summation from I going from 1 to n, as the number of particles are there, and similarly you take the summation here, mi will be inside and summation will be there. So this quantity and this quantity, we get this equation number 8. Now, let T be the kinetic energy of system of n particles. Then kinetic energy is given by, for the ith particle, the kinetic energy will be 1 by 2 mass into velocity square. And for n particles, the summation of all. Now differentiating equation number 9, 9 means this equation, with respect to Qj, we get del T by del Qj is equal to Mi, because derivative Ri is function of Qj's. So that is why we write here, uh, twice comes here, then 2 goes with 2, Ri dot, and del by del Qj of Ri dot. We get this expression. So this kind of expression, you can put that equal to del T by del Qj. Again, if you differentiate 9 with respect to Qj dot, in that case, you will be having this quantity. But you know, del Ri dot by del Qj dot, we have proved this result in lecture number 19, that del Ri dot by del Qj dot equal to del Ri by del Qj. So in place of this, therefore, in place of this, we can simply write this del Ri by del Qj, and consequently, we have del T by del Qj dot is equal to MIRI del Ri by del Qj. Further, from the knowledge of those generalized forces discussed in lecture 19, delta W, the work done, is given by Qj del delta Qj, summation j going from 1 to n. By definition of generalized forces, we write here, if Ri is the function of these, then delta Ri, you know, we can write it like this. In fact, the summation must be there. We are finding it on all particles j going from 1 to n. So the same term is written here, in fact. So delta Ri gives you this quantity. And you know that delta W is force into this displacement. And if you substitute the value of delta Ri over here, so you get delta W equal to this quantity. So if you compare this 16 with 14, so you get value of Qj equal to this quantity. So now you use the results in 10, 13, 17 in equation 8. In equation 8, equation 8 is here. If you substitute the values of these, because this term has become now the Qj, and you substitute the values of these terms. In fact, we know that this becomes the del T by del Qj dot. This term is in fact del T by del Qj dot minus this is del T by del Qj. So you substitute these values in 8 from equation 10, 13 and 17. You substitute the values in 8. We get this equation 18. And this equation 18 is called the Lagrange's equation of motion of second kind. So that was the situation, and that was the result we want to obtain. You can see the statement of theorem. So this was the result we wanted to obtain, and we have derived this result in equation number 18. Now, the corollary. Lagrangian equation of motion in case of conservative forces. Conservative forces means where the potential depends on the generalized coordinates, not on the velocity and time. Not on the velocity and time. So how this Lagrangian equation of motion changes in case of conservative forces. So first we derive it for the holonomic system as we have done in the theorem. So we get this this expression. We call, suppose here it is 19. When the forces are conservative and their system is specified by n generalized coordinates Qj, j going from 1 to n, then we can find a potential V. You know that potential energy depends on the coordinates only, means on the position only, not on the velocities and time. So V is depending on Q1, Q2, Qn. And we have already done this thing, that delta W means work done is derived from the potential, is at the cost of potential. That means delta W is equal to minus delta V. Now if you open this, it where this delta W comes out to be this, and delta W is this quantity. But when you open this delta V, that value of delta V, that comes out to be in this form, because V is called a function of Q1, Q2, Qn. So if you simplify this, we get this quantity. In left hand side, we are getting this. Consequently, Q1 is equal to minus delta V over delta Q1. Q2 is this, Qn is this. So in general, if we write Qj, the Qj in fact becomes equal to delta V, del V over del Qj. Now, if you substitute this value in Lagrangian equation of motion, then this equation number 19, this equation number 19 here, you substitute the value of Qj over here. What is Qj? Qj is del V over this del Qj, minus of del V over del Qj. Then equation 19 takes this form. So in fact, the Lagrange's equation of motion for a conservative system comes out to be this. It is given by equation number 25. Now move on to the corollary 2. Let L be the Lagrangian of the system, then we denote L equal to T minus V. T is the kinetic energy and V is the potential energy. So in fact, you should keep in your mind, this is very important term here, Lagrangian. Lagrangian of a system is given by L equal to T minus V, means kinetic energy minus potential energy. So now, if you look at the situation here, del L by del Qj dot is equal to, you are differentiating in fact this equation with respect to Qj dot. So you get del T by del Qj dot minus del V over del Qj dot. So, but you know, V depends on Q1, Q2, Qn, not on the dots, Q1 dot, Q2. Therefore, this part is equal to 0. When this part is 0, so you can say del L by del Qj is equal to del T by del Qj, this del L by, yeah, we are now differentiating it with respect to Qj. So we are getting this quantity. So from here you have obtained the value of del L by del Qj dot and del L by del Qj equal to this quantity. Therefore, from 25, equation 25, what can we do? We write this del T by del Qj dot. We can also write, this is in fact Qj dot, here this is dot. So because del V, you know that del V over del Qj dot is 0. So you can write here del V over del Qj dot. So in that situation, you are getting this quantity here minus del Qj, because from here you can have T is equal to L plus V. From here you can have T equal to L plus V. So here you are writing L plus V Qj dot here, and del by del Qj, in place of T you are writing T L plus V. Now you know this is del L by del Qj dot, del V over del Qj dot. So in fact this quantity is 0. What I was talking about, del V over del Qj dot is 0. So this is 0 minus del L over del Qj minus del V over del Qj is equal to minus del V over del Qj. So in fact it has already become 0. And this quantity del V over del Qj goes with this quantity. This is on same on both sides. So what we are left with? We are left with this equation. D by dt del L by del Qj dot minus del L over del Qj equal to 0. This is the Lagrangian equation of the motion, and L is the Lagrangian of the system. Lagrangian of the system. So you can compare this equation with Euler's equation, because in Euler's equation what we have done that d by dx and curly f by curly here y dot minus curly f, del f over del y equal to 0. So that was the Euler's equation, and here this is the Lagrangian equation. Why we are calling it Lagrangian? Because here we are using this term L, and that is why this is the Lagrangian equation of motion. Next is the definition of cyclic or ignorable coordinates. If the Lagrangian of a system does not contain a given coordinate Qj, although it may contain the corresponding velocities Qj dots, then coordinate is said to be cyclic or ignorable. The meaning of this is that If the particle pi is specified by the position vector r, and let it is specified by q1, q2, these are the generalized coordinates, three coordinates, and then q2 dot, q1 dot, and q2, q3, and q4. So dot 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 here. So you can have, you can see that q4 is not there, but q4 dot is there. So therefore we can say q4 is the ignorable coordinate over here. So this is the definition of ignorable coordinates. Then we uh, see the Lagrangian equation of motion in case of cyclic coordinates. So in case of cyclic coordinates or ignorable coordinates in L is not a function of generalized coordinate qj. That means del L by del qj will be equal to 0, because L is not depending on qj. And consequently, the equation number 26, which we have seen in the last slide, that becomes d by dt equal to del L by del qj dot equal to 0, right? Now you know the T kinetic energy is half of mass into velocity square summation, because we are talking about all particles. So if you take del T by del V, it is in fact mv, and mv is the linear momentum, total linear momentum, mass into velocity. This is the one situation. Now if we talk in terms of generalized coordinates, then T is equal to half mass into velocity square, because the generalized velocities are given by qj dots. And from here, if we take the derivative with respect to t, if we take derivative here, in fact, it becomes del t by del qj dot, that is equal to 2 times is there, then mass qj dot, that means mass into velocities are there. So in fact, we are calling this at pj. Pj means the generalized momentum. A summation will not be there, mqj, this is the generalized momentum. Why summation will not be there? Because we are differentiating it partially with respect to qj dot only, and here summation is ranging from j going from 1 to n. So that is why this quantity is equal to pj. So that is why del t by del qj dot is in fact del t by del qj dot is in fact equal to pj, and here pj is called the generalized momentum, that is mass into generalized velocity. Now you see Lagrangian is given by t minus v. So del L by del qj dot, again we are doing here del t by del qj dot minus del v over del qj dot. But you know this quantity is 0, and this del t by del qj dot is equal to, this is equal to pj. This is equal to pj, that is the generalized momentum, where pj is the generalized momentum. So now this del t by del t del qj dot can be put over here, because in this case this del L by del qj dot and del t by del qj dot, these are equal, and they are equal to pj. So that is why in this equation we can put pj dot, and it gives you d by dt pj dot equal to 0, and derivative of pj with respect to t is 0. That means pj is constant. That means the generalized momentum remains constant. So you can say generalized momentum is conserved. Generalized momentum is conserved. So that is it about this lecture here. So